So this problem is a rigid body. And this is kinematics, which is motion. So we're just going to say rigid body motion. Okay, that's the type of problem that this is. So don't call it angular velocity, angular acceleration, because that's a specific type of problem that's involved in this. But this isn't angular velocity and acceleration anymore. They're just asking you for that. All right. So rigid body motion. When it comes down to rigid bodies, you got to understand something. Rigid body motion is based on relative motion. Okay, it's literally based purely on relative motion. Make some sense? So what do I mean by that? If I take two particles, let's say I take a particle A and I take a particle B, right? And they tell you that particle A has a velocity like that, they call it v of A. And then they tell you that particle B has a velocity like that, they call it v of B, right? Then what they can do is, oftentimes what they'll do is they'll draw this triangle between A and B. Dang, I don't like it when it does that. They'll draw that triangle between A and B like that. And then they'll say, what is the velocity VA as seen from B? Or they'll say, what is the velocity VB as seen from A? Does that make some sense?
Yes.
All right. So based on that, I'm going to backtrack a bunch because I don't like having the purple written over it. They could say V, and then we'll do B is seen from A, whatever. B is seen from A. And the equation that we know from relative motion says B is seen from A is going to be equal to VB minus VA. Okay, and this is a vector equation, which means that you have to break it into directions. Are you following me?
Yeah.
Okay, this equation that I just wrote up is our bread and butter. Okay, like this is what we're going to be using to solve all of this all of the stuff that we've been kind of working on. You follow me? So what we're gonna do is we're gonna set up stuff, and I'm gonna leave that right there in that box, and I'm gonna kind of redraw this diagram right here, but except I'm gonna apply it to our situation. Does that make some sense?
Mm-hmm.
The problems that we have are literally that same situation, but we have one more constraint. So it's based on relative motion, but there is a constraint. Now, oftentimes a constraint makes a problem easier.
Wait, well, I'm sorry, not to interrupt you, but are you like writing on this board right now, or you're just talking?
No, I'm writing on the board.
It's not. Yeah, I can't see it. I just see the last thing I see is A, V of A, B, V of B, and then the VB slash A equals, and it's just frozen. I don't know.
All right, hold on. Let me close.
Okay, I see nothing. I see it now. I see it now.
It popped up?
I think it was just lagging.
Okay,
Yeah,
no,
you
it
have a
might have been
square
me.
that has V of A. Okay,
There you go. You see like the blue box and everything?
Right. Yes, I do now.
All right, dope.
But there's a constraint. Yeah.
There's a constraint. Now, a lot of the time, a constraint makes a problem easier, but in this case, the constraint actually makes the problem harder. So I'm gonna show you what I mean by that. What we're gonna do is we're gonna draw. So what we like to do is we like to draw rigid bodies. Forget all that writing. We like to draw rigid bodies as 2 points connected by a line. So I'm gonna draw the exact same situation we have here. So we got a dot A and a dot B. And then I have no idea if that's gonna go. So I'm just gonna use the thing. And we connect them with a line. You follow me? So we'll say the line itself is a rigid body. But what we're doing is we're not looking at the whole body. When you look at the whole body, you'll need to use calculus, and you'll need to use vectorial calculus with geometry, and it's really, really difficult. And ain't nobody doing all that work. So instead, what we do is what we're going to do is we're going to follow the 2 points, 2 of the points on the rigid body. So we take any 2 points, A and B. All right. Most often, it is the end. It's the end of the object. Okay. So it'll be the 2 dots like that, like how they show in the problem. Typically, that's what we do. But as we get more advanced problems, especially when you guys, because you're probably going to start doing Coriolis effect next class. And so the Coriolis motion, you actually won't be using the 2 edges. You'll be using a 1 edge point, and then you'll be using like a slider or like a central point. And that's going to make it not really more difficult, but it's going to add a term to the problem. But if you understand what we're going to go through today, it won't be too hard. All right. So the point is we like to use 2 points in the body. Typically, it's the 2 endpoints. All right. All right. Now, what we're going to do is I got to teach you the velocity, and then from there, I got to teach you the acceleration. First thing that we're going to do is we're going to break everything down into to the different types of motions. So I'm going to say all motion. I'm going to put it in I'll put it in purple, whatever. So first we got to understand motion. And this is going to go for everything from now on. All motion is divided into three sections. It's three things. Technically, it's two things. Is within three terms. First term, translation. Okay? Translation is everything that you've learned up until now, all your particles. Okay? So translation is good for particles. Okay? And non-rotating objects, obviously. Non-rotators. Non-rotation. So everything you know up until now goes into translation. Secondarily, which is what you've just learned, which is probably why you still think that it's actually angular velocity and acceleration, because you just came from it. And a lot of time the professor doesn't necessarily explain what they're doing, is the rotation. Okay. And this is where you start looking at rotating / orbiting objects. Now I like to distinguish between rotation and orbit by like this. I'll say like this. Let's say we have the sun, right? And we have the earth. When the earth is going around the sun, this is orbit for me. So whenever something is going around something else, I call that an orbit. You're not going to always hear orbit. I say orbit because I like to be very, very distinct with it, because I don't like to have my students be confused. I read plenty of problems when they say rotating, and I'll be thinking, well, is it rotating about itself or is it rotating about something else? So the whole idea is if it's rotating about something else, I call it orbit. If it's rotating, if it's rotating on its own, let's say we have the earth and there's an axis here and the earth is actually rotating around its central point, this is what I call rotation. You follow me?
Yes.
Now in class, they're just going to say rotating, but I like to be very specific because that's just how I am. So rotation has to do with rotating and orbiting objects. Now, here's the thing. All of rotation is actually based on, you remember your normal tangential coordinate systems?
Yes, I remember them. But then I think one thing that I would be confused about is that, like, how, when it's perpendicular to like the x-axis, right? It's like it's not applied in there, but you can still have a normal force. That used to confuse me.
Yes, exactly. So all of rotation, no matter what it looks like, is actually based on normal tangential coordinate motion that you learned. And so we're going to briefly go through it, and I'm going to turn the normal tangential coordinates, the numbers that you learned, into, I'm going to literally turn what I write here, I'm going to turn it into this. You follow me? So I'm doing all of this for a reason. I'm setting you up so that you can understand what's going down, because going from velocity to acceleration.
No, so I do remember that though. So I remember that, like, literally you have to use like b of x and like use those, and then you have to get the magnitude of the terms, I believe.
Good. So you know that the tangential is going to be the derivative of the velocity. And then you know that the normal is going to equal v squared divided by r. Dope. Now what they did was, this is what
would it be velocity, or would it be velocity, or would it be like rho, or I forgot. It was either rho or one of the Greek alpha. Wouldn't it be alpha or not?
It was rho. You're right. Yeah. I just use r because whatever, but you can use rho. All right. So I'm gonna say this.
Because my teacher's really like specific about that.
Oh, really? Okay.
I don't know.
That's good to know. That's good.
Otherwise, she thinks that you don't she thinks you don't understand anything if you mess up one thing.
I don't like that, but that's fine. So we're gonna say it like this. These two renditions that I just wrote up, I call those the linear rendition. Okay. There's actually two ways to write these equations. It's the same equation. It's just that you write it in two different ways. So I'm gonna say that's the linear version. That's the one that you learned in class. The one that you just finished learning is actually this. So you have the linear version, and then you have the angular version. Now, the angular version is actually going to involve vectors. So tangential acceleration, instead of becoming the derivative of velocity with respect to time, it's still the derivative of velocity, but we're going to now start rewriting everything in terms of our angular terms. So instead of using velocity, we're going to use angular velocity. Instead of position, we're going to use angular position. Instead of acceleration, we're going to use angular acceleration. You follow me?
Yeah.
All right, dope. So tangential acceleration becomes angular acceleration times r alpha cross r, and then the normal acceleration still exists, but now we're going to write it as w squared times r, and we're going to put a negative, and we're going to write it like that. Okay. So these are what I call the what I didn't read. These are the angular rendition. They're the same exact thing, but notice that the angular ones have the vectors. Whereas the linear ones, they do have the vectors, but we don't really use them like that because we already understand that. So the angular ones, we really want to get a good understanding of everything. So we use magnitude and direction. So we use the full vector. Make some sense? Awesome. All right. So with that being said, when it comes down to this problem, I'm going to say it like this. You see how they ask you for, let me see if I can put it in yellow. There we go. You see how they ask you for the angular acceleration? You can't find it without finding velocity first. And it's always going to be this way. There's nothing you can do about it. You have to find velocity first. Find velocity and angular velocity first. And that's just the way these problems work. So I can't get to the answer until I do a problem beforehand. And that's just the way it is. Cool. So we got to go through the whole velocity stuff, but it's good though. So we can recap. All right. So all motion is based on translation and rotation. And then we're going to do the third one. The last part is what we call, which is what we're doing now, general plane motion. Now, general plane motion is a combo.
Basically X and Y. X, Y, and Z, I guess.
No. Don't think X, Y, and Z. You can, but I want you to think more translation plus rotation. It's trans plus rot. They're happening at the same time. Okay. So the whole idea behind general plane motion, we're going to use this problem. A lot of students, the first thing you do is you identify the type of motion. You're only going to have one of these three. Okay. So the first thing that we do when we do these problems is let's put up a method section. And I think I'll put that in, let's put in orange, whatever. So I'll say method. Step one, identify motion. So my question to you is, for this problem specifically, the problem that we're working on right now, is the object translating? Is it rotating? Or is it translating and rotating?
Would it just? I feel like it's translate. I mean, wouldn't it be translating and rotating like a general plane motion?
You're right, but why would you say that?
Because if I look at the figure, you can see that you see like the velocity that's going like downward and the acceleration going downward. And then but it's also rotating I think it's rotating like on those circular points, which is A and B. Like they both have that rotational aspect, I thought. But it's weird for me because it's hard to identify what that even is. Like, is that a rod? You know what I mean?
It's a rod.
So
it's
I'm only guessing
with wheels on the end. It's a rod with wheels on the end. And the only reason they put the wheels on the end is so that it can slide. Do not worry about the fact that those wheels are rolling. Like, don't worry about that. Just worry about the fact that it's a rod that can move.
So the rods that can move is not the reason why it's general plane motion though. So I don't really I don't really know that.
Perfect. All right. So there's a way to know what it is automatically, like every single time. And this is what I tell students. So first off, this is general plane motion. You're right. This is general plane motion for sure. And we need to know that to do our problem. Now, here's the thing. I'm going to say it like this. Once I write up this equation, you can assume everything's general plane motion and just solve based on that because general plane motion will solve for everything. It's just that it's harder. And so a lot of students try to identify what they're working with in the beginning. How do we know it's general plane motion? Take a look at what they did over here. You see how they put this section right here where they put the A and the VA and they have it going down? All right. So what I'm going to do is I like to actually draw those constraints on my object. So the A, I'm going to put these two little parallel lines going down. What that means is that my A can only move up and down. Does that make some sense? And you're going to see people do that because that's going to help them understand. So we know that the velocity of A is going down, and we know that it's 6. So what I'm going to do is I'm going to just write it over here. Actually, I'll write it a little bit later. I drew VA right there. You see how I drew that arrow? Now, look at the part B. Look at this guy right here. Forget the fact that it's rotating. I don't even want you to think about that. This is how we're going to figure out if it's rotating or not. Look at this. B is touching the ground, right? Have you ever seen an object? Have you ever seen an object in this shape where the bottom part literally lifts off the ground like that? Like automatically for no reason? No. Well, normally what you see is if this guy comes like this, then as it rotates, this guy will come a little bit like that, and then B will be like that. And then maybe a little bit later it'll be like this, and then B will be like that, and then finally it'll be like this, and then B will be laying straight on the floor. Does it make some sense? So from here you can see, based on the drawing that I just did, you can see that it's rotating based on the three figures that I just drew. But you're not going to have that on the problem. What you do have, though, is your understanding of the real world. And in the real world, B basically, in every single one, actually, let me show you. In every single one of those situations, look at B. B is on the ground. It's on the ground. It's on the ground. It's on the ground. You see that? So B is actually moving to the right. You see it? So forget all of this other stuff that I drew. I want you to think about the real world and how life works, because dynamics is based purely on how life works. And I want you to identify the fact that B actually is going to have a velocity going like that. I don't know the velocity, but I do know it's going to go to the right because that's just the way the world works. Does that make some sense? Now, a lot of students, they get upset with me when I start doing this type of stuff. They go, yeah, but in the class, the professor does. I say, listen, that is noise. You got to remember something. Back in the old days, for them to figure this out, this is what they were doing. They were going, well, this is what I see when I'm working on this stuff. This is what I notice. And so I'm going to make the math based on that. Students oftentimes get messed up because they think you have to do the math first. Dynamics is not based on math. Dynamics is based on science, which is based on observations. Okay, so always think about the real world first and then think about the math second. So what I'm going to do is I'm going to put these little parallel lines on the B, because that means that B is only going to be able to move to the left and to the right. You follow me? All right, so A can basically only slide up and down, and B can only move to the left or right. Now, of course, you could pick up the rod, but I'm saying if you just let the rod fall naturally, A is only going to go down and B is only going to go to the right. Make some sense?
Yes.
Perfect. So I just drew a velocity on B that wasn't drawn in the situation, but I know that BB is going to go to the right. Like, this is a known situation. You follow me? You have to know that to get the answer. If you don't know that, you can't get the answer. And so this is like one of the harder parts. Okay. So here we go. Let's talk about the situations on how to know if it's rotating, translating, or general plane. Easy. So if it's translating, all objects, all points have the same velocity. Now, when I say the same velocity, I mean the same magnitude and direction, okay? That's what it means for translation. So what that would mean is this. If I were to draw A and draw B, they would say VA is like that, and it's equal to 6. And then VB would also be equal to 6 and going straight down. You follow me? Now, that's going to be
magnitude and direction.
Magnitude and direction, the exact same velocity. What that means is it's literally just falling without rotating. This basically looks, I drew it badly. This looks like this every time. So as it moves, it's just sliding. There's no rotation. You follow me? That's the translation.
Yeah, or like if I dropped a block, if I just dropped a block onto the ground and I use 2 points on that block, they're both going down.
Exactly. That's exactly right. So that's exactly what a translation looks like. Boom. Rotation. A lot of people confuse rotation with general plane motion. So this is what a lot of professors are saying. They'll call it fixed axis rotation. It doesn't matter if you call it that or not, but to specify, they call it fixed axis rotation. Okay. That way they don't mix up that and general plane motion. Fixed axis rotation is pretty easy. The term fixed is everything. Okay. So I'm going to underline that, because that lets us know what's going on. In fixed axis rotation, all points rotate or orbit. You know what I'm going to say? All points, I'll say rotate / orbit. Rotate / orbit a point,
constant.
Not constant, a point on the body. And you got to know that it's on the body. Okay. So everything is going to rotate or orbit a point on the body. That point on the body is still. It's not moving. Okay. So the velocity of the specific point that everybody's rotating around is 0, but everybody else has a rotation, has a motion. Okay. What that looks like is this. It looks like a piston shaft. A lot of the time, you'll see these types of problems where they'll say, "Oh, there's a rod and it's rotating on its edge." So what that looks like is this: they'll say, "This is point A and this is point B, and this is what we'll draw." To make it fixed on A, they'll draw this little symbol. They'll draw that little D thing around A, and that means that velocity of A equals 0. That literally means that A is fixed. That's the fixed symbol. You follow me?
Mm-hmm.
So A is sitting still. B is going around A like that. Now we're going to say that there's a W of the whole body. But what happens is the whole body is rotating around A with that W. But if you look at B specifically, and here's the thing, you got to now start to be able to go back and forth between the two types of motion. You got to start looking between the linear version and the angular version. So the W term is angular. Okay, this is angular.
Mm-hmm.
But when we look at the velocity of B, the velocity of B is not going to be angular. The velocity of B is going to be linear. You follow me? And so that's how they'll write it. They'll put VB like that. And you have to understand that that's a linear representation. This doesn't mean that B is not rotating. It just means that the point, when you look at the point, you want the point to be moving linear. And when you look at the body, you want the body to be moving angular. They're doing the same exact thing. It's just which part you're looking at is going to determine which variable that you use. Make some sense?
Mm-hmm. Yeah.
Now, honestly, that's not really a big deal, though. We can fix that. We know this. We know that, God, I always forget. It's going to be V equals W cross R as a vector. You follow me?
Mm-hmm.
All right. So as long as you know that, then we can correlate. And you know what I'll do is I'll put it in red because we actually need that. That's like a star equation. VB equals W of the body cross R. And that R, I have to give it some more specifics. But this right here is so important. So important that I'll put it right here, and I'll bring these two back over here. All right. So now let's talk about something. These are vectors. You're gonna need to know how to use cross products. You need to know how to use your right hand rule. Are you good with the right hand rule?
Right hand, no, I don't. I didn't. I think she explained that in class. So
that's fine. Here we go. So what we're gonna do is we're gonna add some more specifics to this so that you can know how to actually use this, because seeing this equation is pretty, but it doesn't mean anything if you don't know how to use it. So we have three vectors, I, J, K, right?
Mm-hmm.
Now, I is the X direction, J is the Y direction, K is the Z direction. We're gonna do a clockwise circle. This is the cross product circle, okay? The direction that you go is gonna determine what's the cross product gonna be. So if you start on I and you cross J, you're gonna end up, hold on. You start on I and you cross J, you're gonna end up on K. I cross J equals K. You see how that works? All right. If you cross J with K, you're going to end up on I. J cross K equals I. And so naturally, if you cross, I'm going to erase all this anyway, so whatever. If you cross K with I, you're going to end up on J. So K cross I equals J. You follow me? A lot of students are just going to remember I cross J as K. Cool. Good for them. I don't recommend that you try to remember too much. There are certain things that you have to remember. Like this, the stuff that I put in blocks, you got to remember. Don't worry about I cross J equals K. Just worry about the fact that of how to draw the circle. Okay. So I'm just gonna put up the circle, and then you gotta just know how to use it. So all you gotta know is I, J, K, and that it moves in a circle. That's your cross product circle, and then you're good. Follow me?
Yes.
Now, of course, it's positive if you go in the right direction, but it's going to be negative if you go in the opposite direction. So if you flip the arrows, these are going to be negatives. You follow me? The answer is going to be negative. So what that means is
negative I. Okay.
What happened?
Negative I times K equals J. I mean, like, will negative I times negative K equals J, I guess, or negative J? Or am I wrong?
You said it right, but don't remember it like that. Don't think that the I and the K and the J are negative. Think that the end is negative. So it looks like this. I cross K. Don't think negative I cross negative K. Just think I cross K, but you're going backward, is negative
The total
J.
answer is negative.
Yes, and that's how the negative version works, okay? Now, what you said is right. You could say negative I cross negative K equals J, but that's like nobody says that. So
Negative,
don't even
positive,
think of that.
negative.
Yeah, don't even think of that. So just think you're always going to be using the positive version of IJK. It's just that the answer is going to be positive if you're going clockwise, and it's going to be negative if you're going counterclockwise. Cool?
Mm-hmm.
Cool. And that's how you use the cross product. Now, you need that because that's going to be applied to your W cross R. I'm going to say it like this. W is always going to be in the K direction. Always. Always.
Mm-hmm.
It's going to be plus or minus, but it's always going to be K in this type of problem. Always. Okay?
Mm-hmm.
Like, that's non-negotiable. There are no problems at this level where W is not K. Yes, later on, W becomes more complicated, but that's like most classes don't even cover that stuff in this class. For this class, right now, W is always going to be K. All right?
Mm-hmm.
So, let's say B. I know it's not really drawn properly, but let's say B were, I'm just going to give you an example. Let's say W equals 3K and R equals 4J. Then what you're going to have is W cross R is going to be 3K cross 4J. Now what's going to happen is the two numbers multiply. So it's going to give you a 12. But then you have to do K cross J. What's K cross J? Think about it. If you have a sheet of paper, do it for yourself because I don't want to have to do everything for you. You got to be able to think on your own.
I mean, wouldn't it just be I? It would be I, but then we're going in the what direction? I mean, so are we going? You're doing that? Is that example that random example going off that diagram right there?
No, this is a random
Or
example. This is random. This is completely random.
Okay, well, I mean, so let's say it would be I, but I'm assuming it's positive because we're just gonna act like we're going in that right direction, I guess.
Almost. It's negative. I, J, K. You did K cross J. That's going to give you backward negative I. And that's how you do the cross product. You follow me?
Oh, so the way they're timed, like in the order, okay, that matters. Okay.
Yes, the order. Yes, God, the order matters so much. The cross product is completely based on geometry, which means if you do not do it in the right direction, you're going to get the wrong answer. Because obviously, if you do K cross J, you're going to get positive I. Like if you do this, then you're going in the opposite direction. So you get positive I, but we didn't do that. We wanted the reverse. And so because of that, the direction means everything. And so you see how I'm doing this? I literally came up with this negative almost out of nowhere. I didn't come up with it out of nowhere. I just used what I know. And I'm going to be doing this type of problem. The one that we're doing right now is if you can't do this, you're never going to get the answer right. If you can't do this, you're never going to get the answer right. I assure you. But does this example make sense?
It does.
All right, great. I'm going to erase it because it's taking up all my space. Actually, you know what? Yeah, I got to erase it. It's taking up all my space, but all this other stuff, we need it. So what I'm going to do is I'm actually going to take this, delete it. I'm going to put a new box because you need that whole segment of information. And I'm going to shrink the box a little bit. God, I love this computer. All right, so you need all of what I just put in that box. Cool? So far, you got to know that by heart, and you got to know this by heart. Everything I just said, those are the two things you have to know by heart, okay? Now, let's see how all of this is applied. Remember how I said, this is all based on relative motion?
Yes.
Let's take the relative motion and figure it out. If you look at these two points, don't look at the object, look at the points A and B, right? This right here is going to correlate the variables, but I want to start correlating the points themselves because right now I have an understanding of the VB as it relates to W, but I don't have VB as it relates to A. Does that make some sense? Oh, one more thing. I almost messed you up. Take a look at this R. This R is always going to point toward the velocity you're looking for. What do I mean by that? I'm looking for VB, right? I'm looking for this guy. Your arm has to point toward it. So your arm is going to point like that.
Okay.
Always. That's always going to be that way. So this is going to be R and you're going to see AB. That's how I write it. Some people are going to write it like R, B as seen from A. I can't tell you what your professor is going to do. I can't tell you what you want to remember. If you've seen either one of those, then just remember it. The most important thing is not how to
But
write.
there's no difference between. And so basically, I get it, and I know the differential, like when it comes to like depending on how the equation is written, but mathematically, like for solving it, is no difference between B of A or A of B.
There's a difference.
Technically,
There's a
I mean,
difference.
and when it comes to like sorting the I figured that. So that part I get, but when I say mathematics, I'm talking about like the numbers I place, dividing, you know what I mean, etc.
They matter.
Well, not dividing, but you know. Okay.
Because B of A points, B as seen from A. This is how I look at it. I read it because a lot of people don't know how to read it. Read it like this. B as seen from A.
Point of view.
Make some sense? This is A as seen from B. So they're reversed. I don't like to use these symbols. I don't like to use those, but I know how to read them. So I never have issues when I'm in a class. So I always tell students, read it like that. B as seen from A as seen from B. You'll never hear me go B from A or A from B. B as seen from A and A as seen from B. You won't hear me say B from the perspective of A. No, I always say B as seen from A as seen from B. I just taught myself to do that and I never mess it up. Okay?
B is seen from A is seen from B.
Exactly.
Okay.
So B as seen from A. Look at this. B as seen from A. When you say from A, it means you start at A, go to B. That's B as seen from A. But I don't write B as seen from A. Oh, you know, I'll do it. Whatever. B as seen from A. If you want to do A as seen from B, as seen from B, look at A. That's A as seen from B. So it's reverse. Make some sense?
And that's just in this scenario.
Yes, exactly. That's just in this scenario. Now, this is going to matter because when you put the right numbers in, if you put in the negative number, you're going to get the answer wrong. If you put in the positive number, you're going to get the answer right. So you got to know which one to do. And so it becomes very technical. Okay. All right. So I'm going to move this to the side because whatever. So now let's talk about the actual velocities. I said everything is based on relative velocity. We're going to say VB. We know this is our equation. VB. Come on. VB equals V of B. Shoot. Always do it backwards. I got to rearrange it. VB of A equals VB minus VA. I always know this. And I think of it like this. Whatever's first minus whatever's second. I do little things to just kind of help myself remember. Whatever's first minus whatever's second. It's always going to be the first term minus the second term. And then I can do algebra from there. Follow me?
Yeah.
So I'm going to rearrange it. If I rearrange, I get VB equals VB of A plus VA. You follow me? This is still the relative velocity equation. This is still relative motion. But this applies perfectly to, this applies perfectly to this situation. Take a look at the velocity of B, right? If you look at B, dang, this is getting hard to see. If you look at B, B, let me see if I can redraw it over here. B is going like this. You know what? Forget that. Forget that. A has a velocity of equal to 0. So this term goes away. You follow me? So this term, this whole thing literally devolves into VB equals VB over A. Which means if you sit on A and look at B, which gives us our unit vector, that gives us our arm. If you look at B from the point of A, this is what I want you to do. Just take your arm and extend it straight forward in front of your body. And now turn your torso. Don't turn your arm, just turn your torso and look at your hand. Does it look like your hand is moving side to side? That's what you would see if you sit on A. B literally just looks like it's moving side to side. Does that make some sense? That proves mathematically why B has to be going. That proves mathematically why we use B in the linear version as compared to the angular version. Make some sense? Your arm is rotating, but when you look at the hand is just moving side to side. That proves the whole situation behind this, okay?
Mm-hmm.
And that is why this right here is equal to that statement.
Yeah, but that's only when it's number 2.
Yes, that's only when it's number 2, but it's all good. Number 3 is easy. Once you know number 2, number 3 is easy. So I did all of that explaining.
Okay. I get what you're saying.
I did all that explaining just to get to number 3. Am I good to erase this right here? Can I erase that?
Yep. Mm-hmm.
Any questions so far?
Not right now. I'm understanding it a lot better.
Good.
So yeah.
Understanding.
I even understand like the 0. I understood why the 0 would be like that, but then in the just the difference in that, like the way you're explaining it, is literally swapping the values of
Yes.
via A, or if it's via B, into number 3.
Exactly. So number 3 is one step more complicated. And here's the thing. If you do not understand this, I don't care how good you are at solving the problem because you know the equation. Just because you know the equation doesn't mean you can solve the problem. If you do not understand this, I guarantee you I can give you a problem that will make you fail. But if you know how to solve a problem, if you know what to look for, I guarantee that there's no problem that I could give you that can make you fail. Everything comes down to understanding, and understanding is not math. And a lot of students mix that up. They think it's all about the math. It has nothing to do with the fact that these are solved. Excuse me. This has nothing to do with the fact that these are solved with math. It has everything to do with what this means and what that means. Does that make some sense in the real world? Mm-hmm. All right. So general plane motion. It all comes back down to me saying, how do you know it's in general plane motion? How do you know when it's general plane motion? Easy. General plane motion is going to be neither. 2 different points have 2 different velocities. That's going to be general plane motion. Okay? Literally, that's the only thing you have to know. Now remember, velocity doesn't just mean the direction. It also means the magnitude. You follow me?
Yes.
When 2 points in an object have two different velocities, that object has to be translating and rotating. So let's use our problem, the problem that we have. We know this is the problem that we're working on. So let's prove it. We know that the velocity of A is going down because we said that A is restricted to move along the wall, right?
Mm-hmm.
We know that the velocity of B is restricted to slide along the ground. You follow me?
Yep.
These 2 are different. They're different. One's going to the right and one's going down. It's got to be general plane motion automatically. That's how I know without even thinking about if it's rotating or not.
Yeah.
This is always going to be the case. Don't think about the fact that it's rotating, because a lot of people go, yeah, but it's rotating. And then they're going to forget the fact that it's rotating and it's falling at the same time. It's falling, but because it's falling, it's rotating at the same time. They're happening together. Don't think about rotating and translating. Forget that. All you got to do is think about, is one part moving at a different speed than the other part? Okay? That's all you need to know. Here's another example for people who don't, because you're not always going to see this situation exactly. You're going to see it in the different situations. So let's say we have a straight bar, just like this, right? But let's say that I drop the bar. But let's say that this side is a little bit heavier. So I'm going to put it a little bit thicker. This side's a little bit heavier. Well, you know, in the real world, if you drop a hammer, the head's gonna turn toward the bottom, right?
Yeah.
All right. So on paper, what that will look like is the velocity of A is going down, but we know that this thing is falling. The velocity of B is also going down, but the velocity of B is bigger. Does it make some sense?
Yeah, heavier, bigger, same.
Exactly. So what happens is a lot of students go, oh, this right here is translation because they're both going down. That's wrong. This is not translation. This is general plane motion because, yes, they're both going down, but this is bigger than the other one. And so what that means is this is actually going to start to rotate a little bit more. Make some sense? And that is the proof behind why the head of the hammer rotates toward the ground. Just because it's heavier, it's going to gain more velocity quicker. It's literally work energy applied to general motion. Okay. So all of these situations that I'm talking about, I can turn everything into a problem. Like I could literally tell you the weight of the head and tail of a hammer and tell you I dropped them, and then I could ask you, after 3 seconds, what's the speed of the head of the hammer? And all of what I just said, I could solve it with dynamics. Everything that I'm talking about is good. It can be applied to these equations that I'm writing, and I could solve it just with these equations and maybe some extra stuff. Make some sense? Like, that's the ridiculous power of dynamics. And a lot of students don't understand that. They think dynamics is like limited. Dynamics is the subject to analyze all motion and force. The only thing is, it becomes more detailed, and so you need more detailed classes. But that's it. You follow me?
Mm-hmm.
All right, so let's get back to the problem. I did all of that just to explain that. But that right there, you need that information. Actually, that wasn't a good idea. I need to move this. You need that information to be able to start any problem. So I had to show you that first and foremost so that we could get going. All right, then I move this. Boom, boom, boom. We're good. All right. So with that being said, I proved that this is general plane motion. We're good. Are you following me?
Mm-hmm.
All right. Step 2. Once you know the motion, you write down the equation of the motion. Write the equation.
Okay.
So translation, it's going to be everything you know. It's going to be, I'll put it like this. I'll just write the equations right here for you. So that way we're not doing too much work. Translation is going to be velocity equals the derivative of position, and acceleration equals the derivative of velocity. Bam. Right? Rotation. Rotation is going to be the velocity of some part. The velocity of your point equals the W of the object cross R from the origin to the point. And then fixed axis general plane motion. And here's the thing, it's really, really easy. Remember I said it's translation plus rotation, right?
Yeah.
So it's going to be literally the general plane motion. They want the velocity of B. So the velocity of the point equals, and we're going to turn that to VB. So let me do a direct parallel. It's going to be written like this, VB, because that's what they're asking you for. They want the acceleration of B, but you got to find the velocity of B. The velocity of the point is going to be the translation of the object. Now, here's the thing. The translation of the object is going to be seen as the translation of another point. That's all you got to do. So look at the translation of another point and then add them together. So the velocity of P equals the velocity of your other point, right? So that's the translation. So what that looks like is this, the velocity of A, because that's our translating point. Think of it like this. We don't know B, even though we know B is translating, because we don't know it, we got to use another part of the body that is translating. And we know that part is A. Does that make some sense?
Yeah.
It doesn't have to be A. It could have been this. Like if you knew that this was moving like that, you could have used, let's call it G. If you knew G, then you could have said VG. Does that make some sense? Yeah. Like it really doesn't matter. It's just that we knew the velocity of A, so we're going to use A. That's the awesome thing about this type of problem is as long as you know any 2 points, you're good to go. So it's going to be the translating part. So that's the translating part plus the rotating part. Now we know the rotating part is this equation. Does that make some sense?
Yeah.
So you literally just add that part. So you go plus, and then you put W of the body cross R from O to P. And this part right here represents the rotation. Cool?
Yep.
And so what that looks like in our problem is plus, and it'll be W of the body cross the arm from A to B. Now, this in your class, it'd be written like this, but I really don't like writing it like that. I really don't like doing that. But in your class, you're going to see it like this. I just don't like doing that. So you're never going to see me do that. I'm just going to put A to B. Make some sense? Boom. So that right there, that's step 2. We know that we're doing general plane motion, so I put up the equation for general plane motion. It's literally mindless. Once you understand the type of motion, everything else is literally everything else is mindless. I promise you. Step 1 is the hardest part. And step 1 had to do with us figuring out the fact that A was going down and B was going to the right. Like if you can figure out that A is going down and B is going to the right, and you know this general plane motion, everything else is easy. All right. Yeah. From here on, it's just math. Just math. So step 3, solve. So what you're gonna do from here is you're gonna solve, right? So first thing you're gonna do is you're gonna how do you solve? Come on, I want to get the circle. There we go. So we're going to solve. That's what step 3 and down is going to do. So the first thing you're going to do is do your cross products. Do cross products. So what that looks like for this problem is, let me move this stuff over so that I can solve the problem with you. It's over. And this is how I do it. I always tell students this. If you do not have a way of doing your problems every single time, you are doomed to fail some problems. But if you have a way of doing every single problem, you are always going to pass. So this is how I do it. I say VB. I literally start writing out every single vector. VB. All of your vectors are going to have 2 segments to them. They're going to have a magnitude and a direction. So you're not going to see me put these blocks. I'm way past that point, but I'm going to put them so that you can see what I'm doing. A vector has a magnitude and a direction, right? So a vector can have 2 unknowns, 1 unknown and 1 known, or 2 knowns. So what does that look like? Do we know the magnitude of B? Do we know how fast B is moving?
No.
Nope, they never told us that. We do not know the magnitude. So what we're going to do is we're going to leave it as VB. But do we know the direction that B is moving?
Yes.
Yes, we know the direction. We know that B is moving in the positive I direction because of this. You see that? Bam. That is the reason why we know it's in the I direction. And you need to know that. A lot of people think that because I really go into details and I really drive this home, and people think that I'm doing too much. The thing is, if you don't understand the little bits and pieces, you'll never understand it. And the thing is, if you understand what I'm doing here, then when you read it in the book, it'll make perfect sense. If you don't understand what I'm doing here, they're going to do it in the book and they're not going to be saying what I'm saying. They're just going to do it. And you're going to be like, what the hell is going on? Okay?
That's how I feel. Yep.
Yep. So I'm just here to explain every little bit and piece. And your job is not to learn the math. Your job is to learn the pieces of how it all works. So then the next thing is I just go bit by bit. So I do VB, then I do VA. Do I know the velocity of A? Do I know the magnitude of A?
Yes.
Yes. What's the magnitude of A?
6 meters.
Perfect. It's 6. Do I know the direction?
Yes.
Yes. Is it going? What's the direction?
J.
J. Is it? Are you sure it's J?
It's going down, so I thought that it would be. Oh, I mean, it would be going. It would be going down and to the right, though.
No. What you said was right. It's just going down.
It's just
down
negative.
It's negative, and that makes all the difference. Okay. That makes all the difference, man. Once you know what you're doing, the negative will literally be the reason that you get a problem wrong. So here's the thing: if you go into a test, you should already know what grade you're going to get. But if you go into a test and you find out that you got a problem wrong and you knew what you were doing, odds are I'm 70% sure that you got that problem wrong because you missed a negative. 70% of the time, that's exactly what happens. I've been teaching for a long time. I've been teaching this for 10 years. And I promise you, what I'm telling you is the gold standard. Like this, I know exactly what I'm talking about. So that's negative J. You following me? Boom, boom. I'm going to say it like this. I'm going to give you some more information while we're going. Actually, you know what? I won't. I'm gonna hold off to the end. Then you go to the next one. So then you go W. It seems like a lot of work, but I promise you, I do this every single time. Because if I don't do this, I mess up. It is so weird. I always mess up. Do you know how fast this thing is rotating?
No, it's not given.
It's not given. But do you know the direction of its rotation?
Yes.
Yes. What's the direction of the rotation? Yeah. I told you before, you always know the direction of rotation. Exactly. You're a smart kid.
It's always K.
It's always K. Always K. You should always assume that W is moving in the K direction. Now, here's the thing. When you get really good, the question is like this. A lot of students spend a lot of time thinking about this. They say, is it going to be rotating up or is it going to be rotating down? It doesn't matter what you put. Now, it matters in the real world. The truth of the matter is it's going to be rotating down. But if you put that it's going to be rotating up, guess what's going to happen? The answer that you're going to get is just going to be negative, but that doesn't make it wrong. It just means that it's negative to your guess. What we're doing right here.
Yeah, because you're making an assumption. The
Yes.
same thing like in circuits.
Yes. Yes. Perfect. This is your assumption. It's just that your assumption is right in terms that it's K. You just don't know if it's positive or negative. So what you're going to see a lot of students do, they're just going to put positive K. They don't want to think about it. They put positive K. I like to think about it a little bit more. So you're always going to see me kind of do this and try to figure it out for myself because I like to do that. So based on this, that's actually going to be a positive K. But if it were going backward, I'd actually put a negative K and try to solve it with negative K. But that's just how I get down because I'm really finicky about the way that I do my stuff. But if you always
Yeah,
put
but
K,
if the problem says something like if the problem said like something like -2 revolutions, right? Then you would like no because the rotation is negative. I
yes,
think,
exactly.
right? Would that make sense?
Yes, that makes perfect sense, and that's exactly what you do. I'd say those problems, what you just said, that makes up that's only like 15% of problems. You might get one problem every 5 problems. That's 20%. That's like 20% of the problems that'll be like that. Most of the problems, though, you're going to be asked to find angular velocity or velocity of B. Like literally, most of the time, it's going to be this guy or this guy. 80% of the time.
Mm-hmm.
All right. The last thing I'm going to tell you, I'm not going to ask you. I'm going to tell you, you always know the arm. You always know the magnitude and direction. Always, no matter what you know it. Period. Okay.
Mm-hmm.
Now, I'm gonna tell you like this: you always have to solve with geometry. So you got to do geometry, trigonometry to figure it out. They're never gonna just tell you, "Oh yeah, the arm is this long." Well, actually, they told us this time, which is very nice. They're never just gonna tell you, "Oh, the arm is this long." You have to use geometry to figure it out. But I promise you, they're always gonna give you what you need for the geometry. They're never gonna go, "Oh, how long is the rod?" Dude, professors don't do that. They can, but professors
Yeah, I
don't.
wrote the 3 in there.
Yeah, they
I
just
wrote the
don't do
3
that.
down.
But yeah, what you did was perfect. You put the 3 in there, and so I'm going to do the geometry. So if we're looking at B, we're trying to find the velocity of B. If you're trying to find the velocity of B, I'm going to draw my arm. Which direction is my arm pointing? Is my arm pointing toward A or B?
Towards B.
Towards B. So now we know that that's going to be what the arm looks like. So if you break it down, it's going to go down and to the right. You follow me?
Mm-hmm.
This is what you're going to have to do every single time. There's no easy way to do this. This is pure concept. You have to turn concept into math. So the first part of the arm, we're going to do the x part. It's going to the right. So that's going to be positive, and we're going to say 3i.
Mm-hmm.
The second part is going to be the j, but it's going down, so it's going to be negative, and you have to write that in 4j. If you don't do that, you're going to get the problem wrong.
Mm-hmm.
If you do negative 3i, negative 4j, your problem is going to be wrong. If you do positive, your problem is going to be wrong. If you do not do very specifically plus 3i minus 4j, you're going to get it wrong, period. And you have to know how to do that based on what I just did. Now, I'm going to say it like this. Some students are able to do the trigonometry really, really easily. Like some students are just going to see it and just know. Some students are going to see it and be like, what am I looking at? I'm not gonna lie. I was a type of student who never saw it. I had to force myself how to see it. And so I'm gonna give you the 3 equations that you need to figure it out. You gotta just know how to use these 3 equations and just figure it out. And sometimes it's gonna take you a long time, sometimes it's not. For me, this part, figuring out the arm, takes the most time. For some students, this part takes the least time. You see what I'm saying? So everybody kind of gets hooked up on different things. But nonetheless, no matter what, you're going to be able to use one of these 3, or maybe 2 or 3 of these 3 to figure out the arm. You've always got to figure out the arm. You got to use Pythagorean theorem. You're going to use the law of sines, which is going to be, Jesus Christ, it's A over the sine of alpha equals B over the sine of beta equals C over the sine of gamma. You're going to use the law of sines, or you're going to use the law of cosines. B squared equals, oh God, how does this go? It's C squared. C squared equals A squared plus B squared minus 2 cosine of gamma. Let me look that up to be sure. But I think that's it. Let me just make sure though. Law of cosines. Yes, I was almost right. I got it wrong. I almost got it right. It's 2ab cosine. 2a times b times the cosine of gamma. I'm gonna say it most often though. Most often you're gonna use a lot of cosines. This is the one that you use most often to figure it out. I don't know why, that's just the way it is. But you're gonna need one of those three. One or two of those three you have to do to figure out the geometry. Okay? I'm giving you a lot of information. It is like drowning, I'm not gonna lie. Like if you have no bearing, this is the hardest thing to learn in the class. But if you have a good understanding, then this should be easy. Do you have any questions so far?
I mean, so I understand what you're saying. But I think I'm just trying to wait to see where you're going with it, because like I was just trying to see how it connects with what my teacher makes us do. Because like I feel like we're going so you're RAB, like I'm getting that, but like for me, like she'll do like, okay, if you do VB of X would be equal to like -6 plus cosine like 4 or 5,
Yes.
times
Yes,
5,
yes,
which
yes.
is
Yes.
I understand that. But I'm trying to just see where you're going with the whole cosine thing.
The reason
I'll
why,
wait, or like if
all right, so this problem is not going to have a cosine. I'm going to let you know right now. And this problem is not going to have a cosine just because of the angle. This is a 90-degree angle, and it's not going to have a cosine.
Mhm.
If this bad boy were at like a 30-degree angle, yeah, you have to do cosine. So we're going to do another problem. I'm going to do a quick problem after this, and I'll show you where the cosine and stuff comes in. Cool? Because this cosine is different from what you're talking about. It's different.
Yeah,
All right. So
I figured that. Yeah.
VB equals, and now all we have to do is literally plug and chug everything back into it. So all of this stuff goes into there. So it's going to look like this. VB was VB in the I direction equals VA was going to be -6J plus W was going to be WK cross R is going to be 3I minus 4J. So now I just rewrote that whole thing with all the stuff that we need. Okay? So do you see these boxes up here that I just drew?
Yes.
There's a reason for everything. You notice how 2 of these boxes have X's? That's going to happen every single time. A vector equation can only solve for 2 unknowns. If you have more than 2 X's, you can't solve it. So, yep, you can only have 2 unknowns. And so when you see me solve my problems, I'm not going to put the boxes, but I'm going to put the checks and the X's. If I have more than 2 X's, I messed up somewhere. You're going to have 2 X's, period. Okay? All right. So you do your cross products. That's the step that we're on right now. So we're just going to do this cross product, and what's going to be these guys. So it's going to be W times 3. So let's just do it in my next line. VBI equals -6J. So we have 3W, and then we got K cross I. What's K cross I?
KO K cross wouldn't that be a positive J?
Good man. Positive J. So you put the plus in front. And then next we're going to do, I'll just delete this line. Then next we're going to do the W cross the 4J. So we got 4W. Then we do K cross J.
Negative I.
K cross J is negative I. You're right. But here's the thing. We had a negative right here. So our answer is going to be a double negative.
That means it's positive.
That right there will kill everybody. I mess that up all the time. I'm not even going to lie to you. That part, be very careful on. So the way I do it is just like how I showed you. First, I put the letters, then I put the cross product, and then I add any extra negatives. Okay?
Okay, yeah.
Easy. So you do your cross products, then you add your like terms. Do cross products, add like terms. Okay, so what that looks like is VB, I need blue, VB, and the I equals, the 2 J's go together. 6 and 3 are going to give me a -3, and that's going to be W in the J direction. Oh, wait, actually, I messed up, my bad. I messed up. I don't have to do that because the 3W can't combine with the 6. It's just going to be like that. All right, so what I'm going to do is I'm going to just erase this J, and I'm going to rewrite it like this. -6 plus 3W, and then I'll put the J on the outside like that. There we go, just like that. So that's what that looks like. All right. So final step, a lot of students get here and then they get lost. This is the step that kills students. They get here and then they go, I don't know what to do, because you're not done. Because this is not the answer. I haven't solved for anything. I still have one unknown, two unknowns. I'm still stuck. But remember, a vector is made of two pieces.
Equation.
You don't, yes, you need another equation, but the vector breaks into two equations. So that's the fourth step. A vector is already two equations wrapped together. Break the vector into the x equation and the y equation. EQN is my symbol for equation. So what that means is this, easy peasy. We say in the I direction and in the, oh no, that's not right. I direction and in the J direction, okay? So in the I direction, all you have to do is pull up all the terms that have I's. So in the I direction, my VB has an I. So I'll put VB equals, none of this guy is I, so we don't work with it. Make some sense?
Mm-hmm.
And then this guy is I, and so we put it here. So now we know VB equals 4W. But notice I didn't put the I direction anymore because the I direction is already compensated for as its own equation. There's no more I in the equation. So we know VB is 4W, easy peasy.
Okay.
And then finally, on the left side, are there any J's on the left side?
No.
Nope. So what do we put?
On the left side, we just 0. Oh.
Exactly. 0. There's nothing on the left, and it equals -6 plus 3W. And now look, you can solve. Now you have two equations, two unknowns, and you can solve this bad boy. Solve, and this is how you solve, and then you're done. You're done. From here, it's easy. From here, you're going to get W equals 6/3, which is 2. And then you back solve that. You plug that back in to this. And that's going to give you 2 times 4, VB equals 8. And we're done. We found the velocity. Make some sense?
Mm-hmm.
And that is how this all works. So that's the answer to our problem. All right.
Okay.
All right.